Start recording. Start streaming. Up. Yes, we should be streaming. Let me unmute so I can hear myself. Audio. And I can hear myself. Okay, so the audio also works. That's the most important part. And we can start streaming. So this is, I think 3 weeks ago, I started something which is DMX controlled DC motor, where I've explained what DMX is, what I wanted to do, but I'll just link it if you want to see it. It was in a previous stream, and I still archive it. So it's not on Twitch anymore because it's older than 14 days. And after 14 days, the streams get erased, but I still have archives, which you can find on stream.q, voodoo.info. See previous parts. And the previous part was called DMX controlled DC motor. Quick summary of what I did. Actually, I can show you pictures because I did install it and we did try it. So I have to find the pictures. This can go away. Up. Remove. Okay, correct folder. Do I have pictures of the clock? I still have no pictures of the clock. Pictures. I think I didn't take any pictures of the clock. Do I have them maybe on my phone? Yes, I do. I do have some on my phone. So let me copy them. But I'm surprised that I didn't have. Okay, I don't know where I found them. So now let me copy them on my computer. As always, a long process. I thought I did, and I prepared myself. I did copy some picture actually of the device we've built, and I've built and I've installed, but I didn't put the other pictures inside it. Up. So mount. Up. So pictures. DSIM, maybe I have it here. Where would the pictures be? Why are they inside here? Ah, I got it. Why I don't have them. I have plenty of pictures actually, so I did do my job correctly, but I didn't put them in the right folder. Okay. Up. Projects. Dachboden, clock jockey, pictures. Up. Let me filter out duplicates. This doesn't look good. Okay, so the pictures. Let's start with what the clock is and what the installation is. Let's switch to 3. Now you can see the clock. And we can actually switch the view so you can even have a better look on it. That should be this perspective. So this should be a bit larger. It's not that large, but still larger. If I do F5, does it? No, it doesn't do anything. Yeah. So this is, here is the clock I'm talking about, and I'm doing the installation in. This is the private club I'm helping out from time to time. So this clock isn't working as clock anymore, but here on the dials in the middle, there's a motor. And that's just a DC motor, and the idea behind that is we can spin the dials whenever we want and how fast we want. And that was the project DMX control DC motor. So now over DMX, the DJ can actually turn the clocks, and he has, I think here, yeah, just on top here, there's a stroboscope, and this flashes at a certain pulse, at a certain frequency, and the pulses are long enough. And by synchronizing the clock dials and the stroboscope, you can have really nice effects where the time either decreases over time with the strobe pulse or increases over time with the strobe pulse. I don't have any video of that because I didn't have any good camera there, and my phone doesn't cope with the strobing. So the shutter and so on, I cannot change them, and it doesn't manage to get this visualization quite quite perfectly. So we don't see the effect it does, but when you're on the floor and when the light switches off and then the clock strobes and the dials turn at a certain speed, so either with slow incrementing time, fast incrementing time, it looks really well. And this is why we wanted to have a DMX control DC motor, because the guy who controls the lights, so it's the strobe, but there are plenty of other lights. The eyes of the robot here are controllable. Here, how the fishes, the tentacle thing here, they also light up, and you can control them individually. That's what we did yesterday. So the device finally looked like, so this is the back of the motor, this is the back of the clock, and the device looks, what we've built, it looks like this. I call it the clock jockey, just for the dials. Let me turn this around. And inside the box, we have the device. So these are just the connection. There's a power switch, a USB charge, because it has an included battery, USB motor, because the motor was controlled over USB. Simply a DC motor, which you plug to the grounds and DC lines. Then we have some LED, which indicated the status, a USB to flash the device if I wanted to change the code, always useful. Yeah, that's the status LED. And the device, I have pictures of the device here. This is what's inside the box. We have an ESP8266 board, so we have control over it over Wi-Fi. I'll explain why shortly, why I wanted to use Wi-Fi. And then we have a step-up booster, so we can provide even more power or more voltage to the DC motor. We have a DC motor controller, which is just an H-bridge, and here on the right we have a battery charger and battery protection, and that's just a switch. And here on the right, so that was on the left, and on the right we just had a status LED, and we have a battery here. And this also comes with, why did I choose ESP8266? Simply because if we look at the installation, so this is the clock. On the back of the installation, we have the second part, which we'll do today. The clock itself is on a spinning wheel, is spinning. And here we have a large universal DC motor, which I had from my washing machine. And this can turn the whole clock. And the effect it has is that not only the dials are turning in the front, but also the numbers can be turned. That increases the effect of having time turning around and having this complete clock turning. It really is a nice effect. And that was actually the first thing I ever did on this clock. And you can actually see it here on the top, on the bottom left, under the clock jockey. We have the part which is already installed, which was my first clock jockey, which actually controls the AC motor, sorry, the universal AC motor. And this is just a motor controller, and I was able, so I could switch how fast it was turning, and with additional hardware, I could actually switch on and off the power supply of this motor, and this way somehow control the speed so it doesn't spin too fast, because washing machine motors turn really very fast, and we didn't want that. So that's the view from the top. From there, this is the inside, and so because the clock is turning, we cannot have power going to the clock, and we need power going to the clock to actually turn the dials. So this is why we have the battery inside the clock jockey, so we have enough battery to give, so we have enough power and we can turn the dials without having a cable going there, because everything is spinning. And this is also why I've used an ESP8266, because we wanted to control the device, and the only way to control it was wirelessly. And the ESP8266 was simple because we have a DMX network, so called E131 or ArtNet, call it whatever you want, just DMX over Wi-Fi. And this ESP can now wirelessly receive the data and control the motor using the battery, and the clock can spin. We didn't try with the clock spinning, and we only tried, so I did the installation with the clock jockey and I put it there. It did. The issue is that it didn't fit in here. The box was too large. My project boxes was just too large, and there was no way I could put my box with the device, with the electronics inside, on the back of the clock. So what I did is just remove the box, put some tape, add the labels again. So here we can see everything. The electronic which was inside the box is now just bare, protected somehow by some tape, because that's all I had there. And now it does fit on the back quite smoothly. And we just have to control to put the DC motor using a USB plug here, switch on the power, where the switch which is there, and it is on the right side here. And this way we can now control over the network the DC motor. Now there was a bug, but I didn't debug it. I didn't find it immediately. When the DJ or the VJ, or light jockey, whatever if you want to call it, the guy who controls the dials, when he switches the motor speed too fast, the ESP resets. Now I didn't check, I had no time at this point to check what causes this. It's not too much of a problem, because if you leave it at constant speed, which is the purpose in the end, it is stable. And if you change the speed too fast, somehow it resets the ESP, but after 5 seconds it comes back online. And so you don't really see the bug. You see the bug if you know where it is, but if you don't know, you just set the speed slowly to the one you want. Don't switch the speed too fast of the DC motor, and then it runs well. But I didn't test why. Maybe when you change the speed too fast, there's some back EMF, or it drains the battery too fast, which causes a dropout, which causes the ESP to fail. I don't know. I didn't test it, and it's really hard to test everything there, because I don't have any equipment except any small multimeter, and with a multimeter you cannot see. It's hard to see if something just drops out, or if the voltage drops low for 100 milliseconds, because the multimeter only checks every third of a second or 3 times a second if something happens. So you would need an oscilloscope to really debug it, and putting an oscilloscope there is quite a pain. So I didn't debug it, and I had no time. So that was the electronics. So that was what we did last time. And again, you can watch the video on streamqvoodoo.info. And the next part is really controlling actually the motor, which is right here, the AC motor, which spins the disc or the plate of the clock. We do already have something, but the thing which exists does only one thing. It turns the clock at a constant speed, which is already nice. This works, controlling at a constant speed, but it would be even nicer if you can control how fast the thing rotates, how fast the plate rotates, and that's the part which we'll do today. And I wanted also to do this, although something was existing, because it's not too much different controlling DC, DMX controlled AC or DMX controlled DC motor. It's not too much different. So what we need, again, let's go back to the bench now. Just clearing out some debris I had on top of it. And let's go to the bench view. Yeah, bench view. So the principle is almost the same, and the code will almost be the same for the DC, for the AC controlled photo than for the DC motor. So we need an ESP to control the speed. So we look at the RF box, and in the RF box we should have plenty of these Node MCU or Windows clones. I don't know exactly which clone it is, and this is the part that really we use. So, I also figured out, so this camera here doesn't do autofocus all the time. This is because it's a DSLR. DSLR don't do autofocus all the time. The camera on the right, which you probably don't see, is a camcorder. This does always autofocus all the time. The trick here is, even in the menu, you won't be able to find how to do autofocus, how to do constant autofocus. But what you can do is record a video, and when you record the video, now it is recording a video, it will try to do the focus all the time. So I don't have to press on the button. And actually there's no now recording, so I cannot show the video while I record it. Seriously? Okay, didn't test that. Now switch off. That's a pain if that's the case. Let me switch to the recording modus. Yep. And if I record now, okay, stupid camera. It doesn't display over HDMI whenever I record. So I will have to do the focus by hand all the time. Or afterwards I will change this and use my camcorder, which will probably do this afterwards. But for now, we will have to do the focus by hand every time I want to show something. So this is the module which we'll use. It's simply an ESP8266 with some flash, because this doesn't have, at least this version doesn't have flash inside yet. Low dropout voltage regulator, so we can connect 5 volts and have 3.3 volts, because this only operates at 3.3 volts, and a USB to serial converter. That's the device. That's what we will use. That will be the first part. Now we don't need any battery anymore, because we will have power to control the motor, and this device will not be put on the clock itself, but outside of the box. So we can have power this time. What we need to do now is also how to control DC motor. It's not the same way that controlling AC motors. We cannot use our small pitch driver to control the DC motor. We need something a bit more beefy and something which can handle 250, 240 volts AC. I have 2 solutions for that, and I don't know yet which one I will use. I have probably some kind of preference. I'll talk about the solution which exists. So the easiest, the simplest solution, but not very elegant, would be to use something like this. This is a solid state relay. I've already spoke about solid state relays in one of my previous videos, and it's the same, almost the same thing than this thing here. This is a mechanical relay. Whenever you power, it makes contact, and this way you can switch power on and off. The advantage of solid state relays is you can switch it really fast, really often, because it's on electronics. It's not mechanical anymore. As the name might say, mechanical relay, solid state relay. And the way to control the DC motor, the way to control the AC motor will be to control how often power goes to the motor. So we switch on and off the power very frequently, and because it has enough inertia, you will not see the motor spinning up and down, but it will have some kind of constant speed. Switching on and off, we could do it like this, but because we do it often, something like 50 times a second, this mechanical relay will make first a lot of noise, because you hear the clicking, and it will wear out really fast. I think they're rated for 10,000 or 100,000 clicks. So this is not a good idea. This is why we can have solid state relays. We don't have mechanical parts. They cannot handle as much currents, but this handles 2 ampere, and 2 ampere are enough for the motor to drive at the speed we want. So we could use something like this. The disadvantage with and this is actually what's currently used almost. There's a variac, I don't know how they're called, variable. I'll show you afterwards what it's called, but there is something which somehow controls the maximum speed, and this is used to the solid state relay powers on and off the device, so between the 0 and the maximum speed we can set the speed. The disadvantage is this one is with this triac, with this solid state relay, is that I can only switch 50 times a second, and this is my only way to, and I can only do on or off for half of a AC cycle, so 100 times a second, and that's the most I can control of. So it does work, and this is what we're using, but for finely tuning the speed of the AC motor, this is not very good. And for that there's something else we can use, and I need to find the box with the AC DC dimmer. I think it's this box. CAN voltage meter. First display, probably this one. So here I have a box with plenty of what we can call dimmers. And I hope, no, it is not inside. I was hoping it would be inside here, but it is not. So this is actually the device which is used. I'll show it on the other camera. This is the device which is currently used for the motor. So with this dial you can set the maximum speed, and how it works inside, and we will see it a bit later on, is on the back here there is a triac, and I'll explain how triac works afterwards, but the triac allows you within a cycle to set when the power goes on and off. This also has a triac inside, but it only allows you to switch on and off on the 0 crossing point. This does allow you to switch on and off at almost any point. This is why this device you can tune more finely. You can have a fine tune. This one allows you only 100 Hertz tune. This one allows you per second, and this one allows you a better tuning. But I wanted to show you one of the possible devices we can use. I'll put it on the side because I know I will be using it. This goes here, this goes back here, and I'm pretty sure I had such a relay. Where did I put it if I didn't put it in my relay box? Where's this actually? Read relays. triac. That's the solid state relays. These are all mechanical relays. And maybe I put it in transistor and driver. Yet another box. Yes, I did put it here because it is also a motor driver. So you see, sometimes parts can be used for several things. And here I put it in motor driver because I intended it to be used as motor driver. But it is kind of more, it is more a relay. Then it should more belong to this box than to the motor driver. We can put this here because we might use it afterwards. Get rid of this and I'll explain what this is. We don't need this anymore. And it's actually the same principle. That's what's useful. Here. Where is the button so I can make the focus? So, focus is made on the device somehow. This is a module with a triac. It's almost the same as this one. And we'll have a look at inside. So this is one of the solutions we could use. This is the triac BTA 16. So this BTA always often means that this is a triac. 16 means it can handle 16 amp. And there is also a heatsink. So I'm not sure how long it could handle 16 amps with such a small heatsink without fan. But we will never use 16 amp. As I said, the 2 amp version was good enough for, it is good enough by far for what we are using. The motor doesn't consume this way too much. So on this device, exactly. I think we will use this device. So we have 2 alternatives. Either we use this one, so we have a triac and we can control within using this triac within a cycle when we switch on and off. We'll see afterwards on the oscilloscopes how it looks like. So we will use this either this triac module, and they call it dimmer module because this is how we dim light, or we will use kind of this device, which is the same inside. If you look inside, you kind of recognize, so here's the triac, and then the things on the side are almost the same. But what I found out is you can actually buy motor controllers or dimmers which look like this. And I've already found the pinout. So that was the pinout. Same thing, but so it's almost the same module, but instead of having a switch, what they provide you with control panel where you can switch on and off the power, and this way you can set the like here you can set how often it is on, and I'll probably show you how it looks like. So this, you can connect it this way. We can actually try it out because we want, and these are the 2 options I have. Either we reuse this module because we also have a digital interface, or we use this smaller module. In the beginning I thought about this because this was lying around and has almost everything we need. And the advantage of this one, we have binding posts here. We have binding posts which allow us to have the 250 volts, 200. So the AC means voltage coming in and then going out. Here we have only these pins, so we would have to add the posts, binding posts ourselves, which I don't know if I want to do or not. Inside here there's a, so this module is a bit larger than this module. Can I actually open it so I can show you what is inside? Or is it, no, it's not. It's bent, the things are bent such a way that it is not easy to do it. So you can see it. It's a lot beefier because this is for, I don't know for how much this is. So the triac is rated for 16 amp. I don't know if the complete device is rated for 16 amps. This is rated for 4000 watts, which is plenty good enough. So the components are a lot beefier. Also the triac on the back is a lot beefier, and the rest of the electronics we can see is actually to provide power not only to the triac, so you can control the triac, but provide power to this board, because this is digital control, so it needs some kind of 5 volts. So here there's a 5-volt transformer providing power to this board. And then this board, using the buttons, can then send a signal how to switch on and off the device. The problem with this module here, I don't have any power to control the triac. I would need external power to actually control this triac. So this is smaller. It has the advantage that it can fit in a smaller case. This has the advantage that it could provide power. But what you have to be aware of is that even if it provides power, it is mains reference. So this is why also I put some tape on the back. Whenever you plug something here, it uses, I don't know what mechanism it uses, maybe a voltage dropper probably. And because it doesn't use a transformer for isolation, this thing is not isolated from mains. This is also why you don't, when it is mounted in the panel, you don't have access to you cannot touch directly the electronics, because the electronics are mains referenced and not floating. So we have to take care of that if we want to fix this issue. And I have several solutions for that. So I don't know. So yeah, we have these two choices. Either use the motor controller I already have, and which will change. Oh, that was the sticker with it. Power regulation. Or control this module. I still don't. I probably will use this one because I have 2 of them. I only have 1 of this one, and this one can be, if we don't use our electronic, we can still use it as normal voltage motor controller with this front end. And actually my front end would be not exactly like this. So this allows you by hand to set how fast this spins. Now if I use this module, we just have to plug this thing again, and we can control the motor using a display. And if we want a fixed frequency, that's perfectly fine. A fixed frequency or fixed power actually. Not power, but yeah, some kind of it's a fixed duty cycle, exactly. We can use this device. So I think we will go with this one. Because of this one, I can still show you how it looks like on the oscilloscope. But yeah, let's look at how triacs work on the oscilloscope. So we don't need the relay box anymore. Let's put it on the side. And what is really important is that we will play with mains. Here we will have mains coming in. Now, playing with mains is always a bit dangerous, so we will wear gloves, like I said, but we will not use the normal mains. We will use isolated mains. This way, it will be a lot harder for me to get electrocuted. And for that, we will use the device. So I have to switch the input. Here, this device here is an isolation transformer. It is actually just a transformer inside with a 1-to-1 winding, and this completely isolates mains from the, so we have a power outlet. This is the output of this isolation transformer, but because of the transformer inside, we've isolated ourselves from mains. This way we have a less likely chance to be electrocuted. If we touch just 1 wire, we cannot be electrocuted. If we touch 2 wires, current can still pass through our body, but just touching 1 wire will not allow current to pass through a body and then to earth, because the earth is eliminated by isolating ourselves by using the isolation transformer. So we do have mains. We can play with somehow decently safely with mains because it is completely isolated. Else, do not to be where we are very aware of what you're doing. So we need mains. We need some cable to connect to mains. Should have several of them. This doesn't look like nice. I'll use this one because it has a switch. Here we have, so we can plug this inside here, and then we have exposed wires, which will go in here. And here it's actually written input neutral and live. Because it's AC, it's not really important what is in neutral and live, particularly when we are not connected to mains. So we have this, and this way I can somehow show you how the output of this looks like and how it works. I don't have a AC motor here. I only had one washing machine I took apart to get the AC motor. But instead of an AC motor, we can use some other device. We can dim, and this is what I'm looking for in the flat. It's this one, because it's a dimmer. We can dim motors, but we can also dim lights. Not all of lights. Most of the LEDs light now are not dimmable. But if you use an incandescent light like this one, this is easily dimmable. And this is only 30 watts, so plenty enough. So we will actually use this dimmable light to control as output and test the driver here. Now, see, pain because there's a plug and we need to plug somehow the device inside here. And also, I don't know, my isolation transformer that cannot deliver 16 amps like mains would be able to, or whatever fuse box you have. I don't remember how many amps it provides, but it's plenty enough for the 30 watt. This 30 watt is not a problem. And we can test if the isolation transformer works. Let me switch. You almost see the, okay, I didn't switch the camera. Let me switch on the isolation transformer. The button is on the back. Yes, it is switched on. You can see the blue display. And the blue display here tells you that how much power it is using. So we have an output of 250 volts, although the input should be 240, and it should be a 1-to-1 transformer. It is not exactly a 1-to-1 transformer, and the output is a bit higher. It's at 250 volts. And here it tells 1 watt is currently used. The 1 watt used is from this device itself. So let's switch back to the other screen. Yes. So here, this is what I wanted to show you. This is an incandescent light, and dimming incandescent light is really easy. Dimming LED light is not easy, because when you drive LEDs, you have switch mode power. Most of the time, you have a switch mode power supply, and the switch mode power supply regulates the power to whatever it needs, and switching on and off the current to the switch mode power supply is not a good idea. This is why dimming LED light is a pain and incandescent light is easy. And somehow I prefer incandescent light, but you cannot get them anymore. You only get LED lights which break as often and don't save so much energy in my point of view. So we have the lights, and if we switch on, it works. Up, you can see it on the main screen camera, and because it is too glaring, I'll equip it this way. This works, and if we look at the power rating, it says 33 amps, 33 watts, because we had at 1.5 watts, so it draws around 30.1 watts. So the rating of the lamp, 30 watts, is quite fine. That was the first part. Now we somehow need to have this here, and I think it's not the proper way to do it. The not proper way to do it, using crocodile clamps just clamp here, up, clamp here. But this is a hazard, because if you use crocodile's clamp, the metal here is exposed. You can still touch the metal. You can still touch with your both thing on the metal. So you could somehow have electricity here. And most importantly, they are not very stable. So if by some hazard I'm just moving away and then getting the crocodile's clip away from here, and then they short, they will create a short circuit or put 240 volts on something which have on the bench, and we don't want that. So whenever I work with something which is higher than 50 volts, I try to play it halfway safe. And we will use this thing here, which is just a power strip where I've cut the cable in the middle so I can have access to the power pins on the side. Yeah, I don't use it very often. You still see the sticker, German sticker, for not putting your fingers, yeah, warning it because it's high voltage and you shouldn't put your fingers inside here. So, and we will do exactly that, put our fingers inside here, somehow, indirectly, we'll use some probes. So, up. Let's open, I don't know how they're called, these things. I call them domino, but I don't know what the real name of this thing is. We are completely isolated. So here there is no earth. The earth is connected to nothing. Even if when you are isolated, you can actually, and I have the option on this isolation transformer to connect earth through, but it's not, there are some cases where you would want that. Here we want really a completely isolated 260 volts. So this pin here and this pin here, which are earth, protective earth, will not be used in our case because we will be completely floating. And you can also see that what I don't find good on this device, and I've ordered from China, so don't expect too much safety on that, is that this has a metal case. And whenever something has a metal case with live, I always put earth on this metal case because I don't know how well it is, the board or the heatsink or whatever is inside is isolated from the case, and I don't want, so there is some kind of film to protect yourself, but there are still some metal parts like the edges. So what I do is I put power earth on this metal piece, on this screw here, which is connected to the case. This way the case is earth protected, and whenever something gets disconnected or some electronics inside blow up and touch the case, it's your fuse box, thanks to the RCD, trigger and protect and cut the power. But yeah, and that's actually how it is at the current installation. We have actually something like this, and here it is connected to protective earth on this device. So we will put some, even if we are isolated, we don't want our fingers to be fried if we cross the two wires in the high voltage. So we will put some nitrile gloves, and this kind of rubber will protect you from that. Box is almost empty, but I have a second box. Up. Before we switch on, let's connect this. Let's connect everything actually. We even have a second switch which you can use here. No, this is zooming. Okay, I'm at the maximum of zooming away, but you still have the overview camera if you want overview. So even if there's no line neutral when it's completely isolated, we will try to keep our colors. This is the output, and neutral is blue, and everything which is not blue, most of the time brown, is live. But whenever you have three phases, you often have black, brown, and gray, but it's depends on every country. I've seen orange, I've seen red, I've seen plenty of colors. The only standard is that neutral is blue. And all the rest, except and protective earth, is green and yellow. All the rest should be considered as line. Up. Ah. So here we have the output connected. Output is connected. Let's connect the inputs. Neutral is on the left. Again, it's not too important for which one is neutral and not for AC. Not have to screw a bit more. Up. So you could actually do this without with normal mains. What we will do afterwards requires us to have isolated main. That I'll show you afterwards. For now, I'll try to connect this, and it's too wide. Connector is too wide. So if I screw tightly. Okay. Up. Now it's all screwed, and now the tug test. We tug on the cable to see if it holds and if it's not too loose. Whoop! The complete bench is rocking. So we don't actually. So yeah, this is the plug for the light, which we can plug on the output. I'll show you afterwards. Show here, and we can plug the input to our isolation transformer. That's the output. Let's get rid of the way. Oh, and we can already see it's written 100 up. Oh, it's hard to see because there's no filter on it, but on this 7-segment display, it's written 100%. And they didn't even put here. Normally, I love to put some red filter because this adds contrast, and the red filter removes the white, the complete white on the, lets the red LED light through, but removes all the others. So the contrast between the white here and the red will be increased. Up. So we know we connected correctly, and the device is still working. Now, if we switch this on, we see there's a red light here. And if we switch the lamp on, we see the lamp is lighting up, and we can actually now, what is the down button? Okay, this is the down button. If we regulate down, oh, it's invisible almost to the eye. Yeah, 80. So if we switch down, we should see the lamp here. This lamp should be dimmed. So let's go low. Up 50. And we see there's some dimming here. Yeah, we can clearly see the dimming. We're at 25%, and there is still some glowing filament compared to switch off. And so this dimmer works, and we will use this dimmer also for AC motor. Now, how does this work? This is what we will see on the output. Let me switch everything off for now. I don't have a plug in here, so switch this off, unplug this. And what we will do now, let me switch camera so I can show you, is to see what is happening. We will connect it to the oscilloscope. Something very important with the oscilloscope. This is the wrong one. These are the two probes. These crocodile clips. These are which will be used as ground reference are actually really connected to ground, and the ground, the protective earth ground. So this is connected to the outside shell, and the outside shell is connected to the ground of the input power. So the to ground meaning really protect, what we call protective earth from mains. The problem is that we will connect to see what is happening inside. We will connect the oscilloscope to the device, meaning we'll connect ground to somehow one of the pins inside here, and we could create a short by connecting this to other pins of main, going through the ground, and then tripping the RCD. If we are lucky, it trips the RCD. If we are not lucky, it blows up the cable or the oscilloscope, depending on what you have to do. So there are a couple of tricks. Either what you could do is cut off the ground or the protective earth from the cable. This makes it kind of floating. The other way to do it is really have the device on the test. But the problem, yeah, exactly. So why I don't do that? This is a solution. Putting protective earth, cutting the protective earth coming to the input power of this oscilloscope. Why I don't like this. This is one of the easy solution. Why we cannot do it here, and what you have to be really aware of is that all the grounds are connected to protective earth. So whatever this is connected to is also will be protective earth. But the most important point, on the back of the oscilloscope, I use the USB power port, and the USB port, the shield of the USB port, is connected to the hub, USB hub, which itself is connected to earth. So even if I cut the protective earth from the power cable coming into the oscilloscope, this thing will still be connected to the ground of the USB hub on the back here, so it will still be connected to earth. What you have to be really aware of. You can, and actually what I would do, I will disconnect the USB, so we're, this is the USB for the oscilloscope. It's written OSCI. I will disconnect it so we don't have any problems. But we should have, because this is completely floating, so it will be referenced to any kind of earth without having issues and without leaking to it. But I will still remove it just to be safe. I'm still connected through Ethernet. So it has a USB port and an Ethernet port. The Ethernet port should be galvanically isolated. So even if the Ethernet port is connected, I don't have any shield, so it's not a problem on the cable, and it should be galvanically insulated. So I still have it connected to the network. We can also try to see, I'll be surprised, in the multimeter. So this is the bench multimeter, which we built last time, in the last episode. And if I touch AC, do I see? This should be a true RMS, so this should also be showing decreasing voltage. And I can show you what what I did since last time is I built something so I can show you what is on the multimeter without showing you the multimeter itself. Remove this. So I need to prepare it. Contracts, multi-dashboard. I need to switch on. Duck. Power cycle, bad USB cable. I hate this switch. Okay, now it is connected. Yes, it is working. Well, now my program is reading the measurements, and to show you the measurements, I will prepare my dashboard. Measure. Yes, we can see them. Let me. Okay. 3 here. Remove this. Yeah, save. Here on the right side we have the measurements from the multimeter. to it. Yeah, this bar is a bit annoying, but you can see the measurements and the type of current we have, and this is the measurement over time. And this is actually the reading of the multimeter. Yeah, I could cheat a bit this way. Up. So you see also what I can see. Let's switch to AC. I didn't try AC though. Does it recognize AC? Yeah, it says current AC, so this works. That's nice. Let's switch the camera. Back to this view and see if this works. So we can plug AC again. AC is plugged in. We see power is going inside here. If we connect AC, we have 250 volts. Does it show? Yes, 253 volts. So the dashboard works. That's quite nice. I could zoom so you can see the value. Visible enough? Let me zoom so you don't have to squint with your eyes. Check, check, check. Up. Let's see, we can still show AC. That should plenty readable. Readable. We are in HD. And yep. So back 255 volts AC. That's the input, and on the output, let's put it to 100%. 100%, barely visible, but this is 100%. If we see the 100%, we are at 155 volts, and now because it is a true RMS voltage multimeter, whenever I go lower, it should also go lower on the multimeter. But it doesn't. I'm at 50%, and it is not lower on the multimeter. And we're on the output here. Maybe because there's no load. Let's switch on the load, switch on the light. Yes, exactly. You need some kind of a bit of load for the triac to work correctly. And we can see that now we are at 170 volts for something like 50%. So it's not completely 50%, but it's maybe 50%, so it's probably 50% on the triac. If I switch down, we can see the voltage go lower, but we can only really measure the correct voltage. Go lower, and we can probably only measure the correct voltage if we have some kind of load. Now I go up with the voltage, and you have even a better view than I do, because I only have in front of me the reading of the LCD of the multimeter. You have a graph which shows the evolution over time. And 100%, and we are back to 250 volts. So we know that this works, and with the voltage, with the true RMS multimeter. With the not true RMS multimeter, I don't know how well it does the measurement. I think whenever it's in AC, it thinks it is in a sine wave, and then just calculates based on the max voltage what the AC voltage is. I don't know exactly actually, but we have true RMS multimeter, so we don't have to take care of this. So this is with the multimeter. We can see that it goes lower. Now we will see what is really happening with the oscilloscope, and I have to switch on the oscilloscope. I can use, let's set the probes correctly. So oscilloscope is on. We don't need the multimeter view again. This is the end. Now I need to show you the oscilloscope screen. For that I have another visualization tool, Osci Capture. Okay. Dun, dun, dun. Project. Let me add the auto refresh. So yeah, the pain with this multimeter is I don't have. Oh, just look to. Okay, I don't have. It doesn't have any HDMI outputs, and it has. You can somehow get the data. Ah, wrong input. This way. Now it looks more smooth. You still don't see it, but I'll show you afterwards. I'm setting the thing up. So you don't need this one anymore, because you don't need the voltmeter, you need the multimeter, the oscilloscope. So it has, you can grab the data over using LXI over either over USB or SCPI. I don't really remember the protocol, but you can get it over USB or over, which is then a TCM, USB TCM interface, the standard interface for measurement devices. And then you can just send commands to get the data. I think it's SCPI data, and when it's over LAN, it's called LXI, although the commands are really the same. So I've built a small script which allows me to do exactly that. And here I have the output of the screen. So, but the refresh rate is really a pain. It's not as I see it in front of my screen. Getting the data takes a bit of time, so you will only have a refresh rate of half a second. But at least you cannot complain, and you can see what I'm doing here. So if sometimes you see it flickers, or if it has wrong data, it's just because the data is being grabbed and converted to the device. Rigol does offer some kind of visualization tool, but it's only for Windows. I'm not on Windows, and it does exactly the same thing as my script does. It grabs the screenshots and then shows the screenshot. So the refresh rate is not a lot better on the official Rigol tool. I just need another oscilloscope with an HDMI output. But for now, this is plenty enough, and you can see what I'm doing. So we will use channel 1. Channel 1 will be on AC. Up, we will put 50 volts per, so it protects somehow the input. We will put 50 volts. We have the bandwidth limit. And now we can connect it. And we are connected, not connected with the power. We will connect it to the outputs. I don't want to unscrew the thing just to get my probe on inside here. Well, this, yeah, it seems, yeah, we'll have to, if we do it correctly. Let's unscrew a bit so I can get my probe also below, so it holds kind of, well, it's not holding well. It needs a load, so we need the lamp to have, I would have disconnected the lamp, but this doesn't work this way. Will I cheat and actually use a crocodile clip? Maybe. Probably. And yes, at the end I will. So, we can switch off channel 2. Channel 2 switched off. Deck one crocodile clip. We don't need size measurements. I just want to show you how the triac works compared to solid state relay. So now we are connected to 230 volts, and nothing should happen because we have a floating output, but I'm always afraid that something will happen, and it doesn't. So we are connected, and 50 volt was not enough. 100 volts, parameter over range. Wow. We are on 10. This times 10 probe. Let's put it in the middle. We can still see it. Tack, tack, tack. So this is mains voltage. We are at 100%, and let's zoom a bit. We see that the oscilloscope shows 50 hertz. You see on the top right corner, 50 hertz. So this is because we are in Europe. Here mains is at 50 hertz. Let me check if I can still hear myself correctly enough. Yeah, sound is good enough. Yeah, so we have 50 hertz. We see that it is not perfectly signed, maybe because there's some kind of noise from this thing, maybe because the isolation transformer is not good enough, maybe because mains is not good enough. I don't know exactly. But we do have some kind of sinusoidal waveform. Now, this is the output. Let's switch on the lamp. So switch this on, switch this on. The lamp is at full power. And if I go lower, you will see how triacs work. You start to see it. What it does is it cuts the beginning of the AC waveform. Let's put it to somehow, that's 50% up. It has issues synchronizing. Let me, and the trigger. Let's put the trigger here. So you see here we have 50%, but it's not completely 50%. How does, let me switch on, how does the triac work? The triac works simply, the triac lets power, it lets power through whenever you send a pulse. And this is what you see here at the beginning of the, let me switch, because I cannot show you with screen capture what I'm pointing at, but I can show you with my camera. So this is the beginning of the AC waveform. You can see that it is not switching on to the AC waveform, and then somehow kind of half after the AC waveform there's a huge load where actually now it is switching on, and the device continues to have power for the second half of half of the waveform, because this is a complete waveform. So we have the upper part and the lower part, and on each of the parts you have so the half cycle, and within the half cycle now, because we're at 50%, we only have after half of this half cycle, so at quarter cycle, we have this switch on. And this is how the triac works. You send it a pulse, and whenever you send a pulse, it starts conducting the AC power until it crosses zero again. This is why at the end of this half cycle, when you're at zero, the triac or the mains is switched on, off, and then it waits for half of this half cycle to switch on again the triac, and then we have half of the thing. So if with a complete cycle, we have 2 times half. And the advantage is here that although we only have 50 hertz or 100 hertz, because we can use it on half of the cycles all the time, although we only have 100 hertz, we can, within this 100 hertz, set really precisely the percentage we want to have. So it's not small increments. And this allows us to dim quite beautifully, because the solid state relay, which I have now, only switches completely on or off half a cycle because of how it works inside. It only can switch on the zero crossing point. And here it doesn't switch on the zero crossing point, it switches on at any point within this waveform. The only thing which restricts your precision is when within this, the resolution of when within this half cycle you're actually sending the pulse to the solid state relay. Sorry, to the triac. And if you have a 16-bit counter, you have a 16-bit resolution, instead of having to switch on or off a complete cycle and have some kind an average good enough. This is why this let me switch again because we are finished. I'll show you again. This we go higher, and we can see that there's more of the AC waveform. This is the complete AC waveform. And now we are decreasing. We are decreasing 50%, 40%, 30%, 20%, up 3%, 1%, and 0%. So now it is completely off and it doesn't trigger at all. We can see that this is trailing edge dimming. There is other ways. Sometimes you don't want trailing edge. Whenever you dim LEDs, you actually want leading edge trimming. We don't dim LEDs in this case, so we can do trailing edge dimming. Oh, I don't know which one is called which one. Here we have the AC waveform at the rests of the edge. So I will call it trailing edge. I don't know exactly if it's the right word, but we will have this power switch on at the end of the waveform. This works fine for AC. This is nice because triacs do that really well, and triacs are inexpensive. And for incandescent lamp and for motors, it is plenty fine enough. Whenever you want to switch LEDs, for example, for dimming LEDs, LED lamps, because of the switch mode power supply, you don't want out trailing the triac way trailing edge, but you want to what is trailing is the leading. You want to lead on the leading edge and then have the whole power. The issue here is that we can see that the beginning it will switch on from 0 volts to 200, even higher to 300 volts really fast, and then it dims. This is not very good for switch mode power supplies. You want to ramp up really slowly and then to cut off really fast. This is why you want the leading edge at the beginning. So you would want leading edge dimming. And for leading edge dimming, you have to use PMOS, which are a bit more expensive than just triacs. Triacs are not expensive, and you can find it a bit everywhere. Leading edge dimming is not, which I would call leading edge dimming, using not triacs is not very popular, and you don't find it a lot of devices. Most of the things which you find, just use triacs because they're easy to drive. So that's how triac works, and we've spent 1 hour explaining that, but we now can work actually on the project now that we have the basis. I will not explain what DMX is, because I did that already in the previous video with DMX controlled DC motor. So if you want to know what DMX is, watch this video. The beginning, I think part 2, probably part 2, yeah, the part 2 explains what DMX is. Now you know what AC dimming is. So let's switch off the power. Up. Let's disconnect. So switch off here, switch off here. Let's disconnect the multimeter. The multimeter. Why do I call it a multimeter? It's an oscilloscope. The multimeter can still be used. Up. I will switch off. Let's switch off this overview. I'll write what we did. Switch off the multimeter. No, oscilloscope. Again, I have issues with that because it makes noise. And this is what I can show you here. Let's switch the camera. Up. This module shows you how to actually use the dimming. So we have 4 pins. Let's try to focus on it. This is the input. So we just need neutral, because whenever you have voltage, you need some kind of reference. Reference will be neutral. Then we have in and out, and the in will be switch on and off and go through the triac. This is just this just provides power for the triac to work correctly. And what we have here are ground, VCC, ZC, and PSM. So ground and we have 2 devices here. These are optocouplers. This part will be completely isolated from this side. This is what the optocouplers are for. We have 2 optocouplers. Yes, actually, it's not exactly optocoupler. This is an optocoupler. This is something which tells you whenever you cross 0. So whenever there's 0 crossing, this device will give you a pulse to ZC, like 0 crossing, and this way you know your reference and when to start. It is not that important though. You could do it without. What's more important, so this is the output of the module, this is the input, the PSM. I don't know what it stands for actually. Pulse signal modulation, I don't know. This will determine when. So when you send a pulse here, this will send a pulse to the triac, you think this optocoupler, and this will switch on the triac. So it is not too important to know whenever there's the 0 crossing, because you just have to send a pulse. You know that the frequency is 50 Hertz. So you just need to send a pulse within this 50 Hertz, and the 50 Hertz is really, really precise. Over a long time, the 50 Hertz of the mains is what is most precise, because this is how they regulate all the electricity. So whenever you have the microcontroller, just set it to 50 Hertz. It is precise enough over time, and just send a short pulse, long enough, I don't know, 10 microseconds probably. I would have to look at the data sheet. Just send a pulse to PSM, and then this will switch on the device. If you want it really precise and to control when within this 50 Hertz you want the 0 crossing, then you could use this. You could use the 0 crossing device. And oh, actually, this pinout. Now we have this module. This is the output. What we have here, I already figured it out. Yeah, high volt, do not touch. They are right. This is mains reference. Here on this pinout, we do the same as here. There is a ground pin, there is a VCC pin, 0 crossing, and PSM. And the pinout is, yeah, the pinout is there. I don't need this finger. Yeah, the pinout is within here. So I know this pinout plus, minus. I don't know actually. Out triac gate. Did I write it somewhere? Gate is N. Ah, here. The pinout is actually already written. SCR, 0 crossing register, ground, sorry, 0 in. So ground is connected to neutral of this box. Then we have SCR, which is actually the, they're called SCRs. Now I get it. The steamers are called SCRs. And this is the triac. The SCR is actually the triac. Then we have 0, which is 0 crossing. And then we have 5 volts. Yeah. So 0 is, it tells you whenever there is a 0 crossing point, and 5 volt is the 5 volt input. The problem with this one, again, is that this will be reference to neutral. So in this case, they tell you not to touch, and you only have buttons. We will have this device, so we actually don't, and it is wireless, so we actually don't really care if it's ground reference or not. The issue is that we cannot plug, I don't know yet. This is the decision I have to make. If I want to have a really superb device And really the nice way, I would have something like this, where I take the 5 volts, but I want to isolate myself from the 5 volts here. And like we did with the multimeter, the bench multimeter, we use a device which isolates the 5 volts, so we are not referenced to whatever this is referenced. So this module would have 5 volts, but not referenced to neutral. So we cannot get electrocuted, or our device cannot get electrocuted whenever we are plugged in. This would be the really proper way to do it. And then you would have to isolate also using optocouplers. Like here, you would have to isolate the input and output. So the solid state, actually, it is at 5 volts. Plus AC, 5 volts, minus AC, 0 volts. Oh, this is how it works. Okay. We would have to, so it uses 5 volts. This outputs 5 volts on also the signal pins, meaning we need to use shift registers or level shifters for this device. Actually, level shifters, we don't really need level shifters. We could use voltage dividers, but the good way would be level shifters. So in theory, I could either connect this directly here, and then I would have to write, this would be in a box, so it's not too important. Actually, do I want to put it in a box? I don't even need to put it. I would have to put it in a really strong box, so nobody can access to the pins and touch by accident. And I would use one of my project boxes. Or I could do it the proper way, the really good way, have a transformer for isolating the 5 volts and have two optocouplers to isolate the 2 signals, and then this could be always connected to the computer, while it is also connected to the SCR. In the end, the idea is that you can control it over DMX and you never have to program it again. So in the end, I really don't need to have it connected to the computer, except if I want to flash it, and I will have to put a huge sticker. If you want to flash it, disconnect this lead because it is mains reference. But this is if this would be my location, and if I expect someone to be able to read labels. At the club I am installing it, I don't expect everyone to be able to read labels, but just plug the USB whenever they want. So I don't trust them to spend the time correctly, or just misread the label or whatever. So what I will do is really isolate myself from this 5 volts here. So we have this problem again, is that we need to have some kind of 5 volts still to provide power here. So we will do exactly like we did last time with the bench multimeter. We will use something which isolates our 5 volts. And this, we only have 1 watt. This is enough. I think this draws 70 milliamps. So 1 watt would be 200 milliamps. This would be plenty. We should have enough power. I don't know how much this can provide. We will have to test it. So before we build the device, and we have to build the breadboards. We'll do the thing on a breadboard, because before I build the final prototype, I want to test on the breadboard if it works or not. So let's begin. Too small. Breadboard. You focus again. That's really a center. It's really a pain that this camera cannot show even when I'm recording, that I have to create the focus all the time. I do have almost prepared here breadboard with lots of pins, so I can directly connect things like that. So the ESP. Where is the voltage input? Voltage input is on this side. Oh, actually you can put it on the middle. Tack. Yeah, voltage input. we will have wires here, jumper wires. Ooh, light is coming. It was gray the whole time and now light is coming. Up. So let's put this switch here. Try to focus. Yeah. Ground. No, not white. Let's use black. We do have some black wires. And red for plus. Although my color code is orange, white and black are ground most of the time, but I use white whenever I don't have any black anymore, and I think I do have a couple of black wires. No, I don't actually. I need more jumper wires. Let's put it this way. Do I have a small black wire? No, I don't. This one is the smallest and it's too large. So let's use white for ground. And let's use red for VN. Check. Check. Now we will use the same thing we did last time, and now I know where it is. We will use one of these isolation transformer. Looks like this. This is a B0505S, 5 volt input, 5 volt output, but isolated. And I never remember what is plus and what is minus, but we can have a look at the data sheet. I think 5 volts inputs, 5 volt outputs. Why did the screen switch off? Ah, the screen switches off always. I don't have the data sheet anymore. That's weird. No, I don't have it anymore, so I'll download it again. B0505S data sheet. Do I have the brand? Monson. Normally the pinout should be similar to across all devices, but I want to be sure. Like with transistor pinouts, it can be different. Three. So this is the data sheet, and I want the pinout. This is the pinout. Is written bottom view or top view? No, bottom view. Bottom view 1 is ground, 2 is VCC. Bottom view, it means that this one is ground in, right? VCC in, ground out. Normally I have another. So bottom view, VN, yeah. And then the output, the second is 0 volts. It's not ground anymore. right spacing, and then second will be 5 volts. 5 volts. 5 volts, so that's the output. And the input will be provided by this thing. So we will use you don't see what I'm doing now. Where is my focus button? Here. We use this long header so we can connect. Actually, why do we put it so far away? I need to put it far away. Up. 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 That will be the connection going in. We have the pin out somewhere here. 0, 5 volts, and we have ground. Okay, goes this way. So that will be the pin out. Up. So we have, will not be the same ground, but which one is this ground? Third one. I don't know if this one has, this SCR has enough power, because it can deliver 1 watt, but it draws more than 1 watt in the input. Nope, sorry, 5 volt is the last pin. 5 volts. We actually need the oscilloscope for afterwards. Now we can try. If we switch on, we should have but we don't. It's not working anymore. Did I do something wrong? Here, no. Let's check if maybe the writing here is not correct. So we'll test with the multimeter. Up. Multimeter. You have the datasheet now, you cannot see the multimeter, but I can tell you what it does. So in theory, let's put it this way, this should be ground, this should be 5 volts. And it is. Let me put you the multimeter so I can read the datasheets while you have the multimeter. I'll see. This stupid device. To power cycle. Okay, I have to change just the hub here. It's not giving me a good connection to my multimeter. So I put this on my screen so I can have a nice view, and I will give you my multimeter. Measure. This is the right dashboard. At some point I need to update our notes. So you have the multimeter view. Fetch check. So what did we say? This is ground, this is VCC. We can see we have 5 volts outputs. doesn't it work when I put it here actually? It doesn't provide enough energy. Let's disconnect this for now. Or maybe there's nothing on my, let me check. Maybe there's nothing flashed on this device. Oh, there is. Blue light is going on, maybe there's some flash. So now we're connected through this thing, so we can test, do we still have 5 volts? Wow, 0.4 volts. Okay. Okay. Means that this doesn't have, this circuit doesn't provide enough power for this device to work. I have no idea how much current we can draw from this 5 volts. If I, let me disconnect this device. 5 volts. Yep. If I plug in, the pinout is right. Ground V in, yeah. Oh, did I see 5 volts? No, 0.4 volts. Okay. Now I don't know if this thing works. This is one of my, this was lying in my box. So I will use my power supply, just provide 5 volts. Yep, power supply on. How much does it need? Just this device. Actually, I can also show you. Can I? Yes. No, I don't want to. Can show you with. I could also show you how much the thing draws, and so we don't need the multimeter anymore. Sheets and I can show you both. Normally, yeah, it does detect it. So up. You continue grabbing from the multimeter. Okay. You start grabbing data from my power supply. Power supply, this one. Thank you. Okay. And now I have to de-zoom because here on the right side, so on the left side you see the multimeter values, and on the right side you see the power supply values. We're set to 5 volts and we see that the output is on and we are in constant current mode. And I've set the limit to 20 milliamps, and we can see that the output voltage is at 0.5 volts. So if I switch off, yeah, so I can change the outputs. Let's see how much it draws. It should be actually in the data sheet. What the minimum, wow, draws really a lot. 100 milliamp. What the hell? Is this intended? $300 milliamp, and we're still not at 5 volts, and this is the input. We have no load on the output yet. I shouldn't switch off the display. I need to see what I'm doing. Is this normal? I provide... that doesn't sound right. I'm providing 1 amp of current. Because it's just a coil, maybe we still have the right output. Let's test this. I need to put my multimeter to connect the multimeter to the output of this thing. Up. Let's use the right colors. That's the output. So clip. I'm connected the multimeter to the output of this isolation transformer. Click. Okay. This is the output. We still have no output, although we are providing 100. And the device is not very warm. I think this is broken. It is getting warm. Did I did something wrong? Ah yes, I switched input and output. This is the bottom view. This is ground. Did I break it? No, I didn't break it. I switched input and output. I just have to switch. Yeah, I thought although it is written on the datasheet bottom view, and I looked for bottom view, I thought at top view. So let's go low and see what is. It draws 25 milliamp. Draws 25 milliamp at least. There is no charge on the output. We only have the multimeter. Let's let the limit 200 milliamp. Normally it's 200 milliamp, so 100 milliamp. Now if I connect the ESP, how much does it draw? We don't have 5 volt output. Sorry. Yep, you will connect here. You will connect here. I hope it doesn't make a short. It does make a short. Up. So now if I connect, let's not connect the ESP for now. Let's only connect. And so we have 5 volt output, 5.2 volts output actually. Now I connected the ESP. Okay, we're at 2 volt output, meaning it needs more than 100 milliamp. We need 5 volts on the outputs. Okay, let's limit at 400 milliamps. So let's see if 400 milliamps are enough. 400 milliamps? No. Needs more than 1 watt output. We see that the output of the 5 volts is at 3.8 volt. It should be enough for the ESP. And we're in constant current mode, meaning the device cannot provide more than this. It should be. It says 1 watt. We are not providing 1 watt. We are providing 0.8 watts. What if I press on reset? LED is blinking. I'm not sure if it's connected to the network though. I'm not sure what is flashed on this device. But having only 3.8 volts, 7-volt output. I'm not sure if it's sufficient. It's not 5-volt output, and I'm not even sure. I have to check. I think this is flashed with something. I will flash it with just stupid VLED, for example. I can actually connect it to my USB. So up. I need USB. There should be a USB cable somewhere here. Up. USB cable. Yeah, okay. So whenever, I don't see what I'm doing. Whenever I have constant power with USB cable, we see the LED is always on and it's always communicating, meaning everything all right on this side. Serial converter, yeah, USB 2. Meaning if this blue LED is not always on, it doesn't get enough power. And we will also see that on the output of the V-in we are only 4.2 volts. There is, I think V-in is after, there's a small diode, so there's a 0.3 to 0.6 voltage drop, but there is still not 5 volts coming in here. It draws too much current. Okay. I don't know how much is used though. Do we flash it? We don't need to flash it. I'll check. Is it connected to my network? You will not see it because it's my network, and I will not show you what is on my network. No, it's not connecting on my network. So it's probably not provisioned with the credentials from my network. I don't know what's flashed on this device. I will just flash something on it, so we will have something. Okay, we are flashing VLED on it. Still flashing. Okay, it finished flashing. Let me check. Yes, we see on our phone here VLAN app, meaning this is here. This is on, and I can use the phone to see if it's on. But actually, we can just use the LED. We now know there is kind of a firmware on it, which gives an access point. So it draws probably a bit more than normal, but we can check this way if it works or not. So let's disconnect the USB, and as soon as we disconnect the USB, we have no power. Let's switch on the power supply. Power supply is on. Okay, the power supply is on, and it is somehow on the output there's only 4.4 volts, which should be enough, but it doesn't start, and we draw only 60 milliamp, which I don't expect to be sufficient. Just connect it correctly. 3 volts. I have set the limit to 400 milliamps. So yeah, this is one of the reasons why I don't always like using ESPs. I don't really use them often. They draw too much current. It's Wi-Fi. Wi-Fi draws too much current now, and now it doesn't even have enough power to start, and it keeps getting stuck. Meaning we cannot use the solution where we draw power from the SCR to power this thing, at least not through this transformer, because this transformer somehow reaches this limit. Now we're at 100 milliamp. It's not the limit of the power supply, but we still have not enough for this thing to turn on. If I hold it reset, yeah, exactly. So if I hold the reset button, we see that the voltage goes on the multimeter. We see we're at 4.8 volts. This is the output, but it's still using some kind of voltage. I think because the reset is just resetting the ESP. We're still powering the USB to serial converter. It's at CH340. And I think this still draws a bit of current. This is why we are not 4.2 volts, but we are at 5.2 volts, which is the output without load of this isolation transformer, but we are at 4.8 volts. And we are drawing 50 milliamp on the power supply, and without load it will be 25 milliamp. So it does power this, but as soon as I release the reset button, tuck, we've seen just a small LED blinking. Let's do it again. We see a small LED blinking, and then it shuts off. It doesn't have enough power. And we see that the power supply powers 160 milliamp, gives 160 milliamp, which goes here, but that's not enough. Now, if I remove the, we cannot use the solution with this. The ESP needs more than that. Let's connect directly the 5 volts to the power rail and see how much the ESP draws. Yeah, that's what I thought, and this is what I did measure the last time, 75 milliamps. It does draw 75 milliamps. Let's see if this can provide 75 milliamps. So, we disconnect the power supply, we connect this, the pin out is written on here, 5 volts is on the left, this is powered, so we should have 5 volts, we will see, and then ground is the second pin. Okay, so we have our answer. Even with this setup, the ESP draws too much power. So we have a solution. We have our answer, which I've asked in one of the beginning. We see we are at, yes, you can still see it. We're at 2.5 volts on the output. The output here, meaning this cannot provide enough current to power. So it's enough current for 7-segment display and the probably tiny microcontroller, really small microcontroller, which is here, and the 7-segment display is probably not lit at the maximum, but it doesn't provide the 70 milliamps, which is used by the ESP to connect over Wi-Fi. So yeah, we cannot use the SCR with, or we could actually use the SCR and connect here, but we still need to power the ESP from the outside. Since we power the ESP from the outside, why not use already this module? Because it's smaller and it's big enough for what we want to do. That's a good question. do we want to do it? Because if this is completely isolated, we need to have an external power supply, so an isolation for this one. So we will just provide power over this mini USB, and then we can connect here. Are these pulled up? So VCC. So we can use 3.3 volt levels, so we don't even need any level shifter. So this would be ideal in the beginning. Yeah, I think this is what we will do. We will not use this SCR. It cannot provide enough energy to power the ESP. We will use this module, and I need to order back this module, because once I use it, I probably want to have another one. Let's connect this back to see if it works. Yes, it does work. See, almost 97%. Okay, so we cannot use the SCR. We will have to use, well, we could use the SCR, but if we use the SCR, we still need to provide external power, which now has not much of an advantage over this one, because this one in the beginning we had the issue that we need external power, and the rest is provided. And yeah, a shame. This VLAN just draws too much current, and this one doesn't provide. What we could do is change the antenna here so we have more power coming out, but I don't want to modify this thing. We will keep this thing just for testing or for fun, but we will use this dimmer module. And I need to reorder it. I only have one of these. We also need good connectors for the input, which, yeah, it's not too much of a problem. I have enough connectors. I think I will use, I have to find them though. Connectors. Terminal block. Did I put it here? Yeah. I think these things are rated for 250 volts, and we will use these connectors. And the advantage of using this connector, I can disconnect it. It's still safe. So if we have the, although not completely safe though, I think the screws are still connected to it. So you can still touch. We will put some shrink tube once the cable is there. So this will be on the motor side and AC side. This will be on the board side. So we will use this, very probably this connector. Oh, wait, I do have something else. I do have this. That's even more. Same thing. This way we can have separate input. So this will be the input. We don't need any. Do we have larger inputs? Yes. We don't need actually. We don't need earth because nothing will be connected to earth. Do we have a connection to earth? Yes, we want to have a connection because the our case will not have a chassis. So we don't need to connect our case to earth because it will be plastic. The issue is that the motor has a chassis and we want to connect the motor to earth. So we need inputs protection. So we need the earth to come through. We don't need just AC/DC, AC signal. So we can use these connectors with 4 inputs. We will only use 2 of the inputs, the 3 of the inputs, and then so there will be one side for AC in. Do we have something? Do we have a connector, an IC connector? Probably, yep. We will probably do it the correct way. I need to find them. Button switches, no. Prog, serial, misc sensor, no. Power resistor, button switches. I think it's in the switch box. My switch box. So I don't know if we will use these connectors. Maybe we will use, we will use this connector. So this will be This will be the output. And is 4 enough? 4 will not be enough for the complete output, because what we have is we do have the AC, which will provide power, so it's 2 pins. We will have protective earth, that's 1 pin, and we will have the tachometer input, because the motor can provide tachometer signals. Yes, it does provide tachometer signal. So it's 2 more pins, and meaning in the end we could connect 1 to ground. I don't want, we will be isolated. It's not wrong to put it to ground, but we will be isolated, so it would be nice if we have something like this, but not for 4 pins, but for 5 pins. But I don't. The maximum I have is 4. We can have multiple connections. One would be for the power output, where we only use 3 pins, like AC, and 1 would be for the tachometer, which would be separate. I have enough of these connectors. Sadly, I don't have only with 3 pins. That would be the best thing. And for the inputs, we will use something like this. Yeah, I still have a few of them. We'll use something like this. So this will be the proper input into our box. Is our box big enough for this? Yeah. With a proper switch, which allows us to completely switch on and off this thing, connecting this through here. I don't know if they're connected left and right. We'll check. So we will be able to provide proper connection here, and then proper power inputs using this way with the fuse and everything we need. The fuse, we will have to change it. I don't know if there's what is inside, but we need a really ridiculous fuse. We don't need a lot of power. We'll probably add a 1 amp fuse, or if I have smaller, we will see. This will be the power input, which is correct power input. Now there's no mistake, and cables for this are ubiquitous. And for the motor output, because we don't have a plug, we will use connectors like this. We will use 1 for 2. The one with just 2 will, we can cheat. I forgot about that. There are no, they're not the same. Well, we will have 1. At least we cannot. Are they interchangeable? Because I don't want them to be confused. Can we put this one here? No. So we will have a large connection, too large connection for the tachometer, and we will have this connection for the power output. I think so. And we will need power. So it starts to be a lot now. I don't know if everything will be in the box. So we'll have the ESP. We need this. We need this. We need this. We need a small connector, so the connection is not too much of a problem. But what takes place is we need some kind of power. Either we have, and this is I think what I will do. No, it's not it's not ideal. 2 solutions. Either we provide external power or we have our own power supply. External power is the easiest solution, but it means that we need to connect 2 things, 1 time mains and 1 time external power. What we can do is just use so here is my voltage regulator box. I have plenty of voltage regulator, and I do have some which provide 5 volts. 12 volts, no, that's not good. Okay. I do have these ones, which take 240 in and 5 volts out, 0.6 amp, plenty sufficient, and it's completely isolated. And I have also these ones, and these ones are a bit particular because they have 5 volt outputs and 12 volt outputs. I think I will use one of these bricks. And I need to test if everything fits in the case, else I need to find another case. We could actually have, I don't have one for just 3.3 volt output, but yeah. So we'll have to put all these devices into a box. Is the box big enough, or do I need another box? I do have other boxes. Worries. But I like to put everything in my project boxes because I have a finished template for that. Up. So, project box, one of the PCBs. It is not large enough for display. Stop switching off. I need to see what I'm watching. I need to go in the menus to stop you from shutting off. This doesn't. Wow. Even this way, it's not enough. See? Even here, I don't have space enough for the cables, and this way, I don't have space enough. So it's not large enough. So I cannot use one of my project boxes. I need another box. Project box. Bye bye. And let's see what kind of small boxes I have. I'm not showing it to you now. This one. All these ones. I think I'll use this one because it has more space. Do I have larger boxes? Nope. And all the other boxes I have are made of metal, meaning I will have to ground them, and there's a potential. I could actually use a metal box. I prefer plastic whenever it comes to high electricity. I prefer metal, even if we ground the chassis. It's one problem, which if the ground connection gets loose, then the chassis could be live. We don't want that, so we use plastic box, which is sturdy enough. This will be the plastic box we will use. Yeah, plenty enough for the motor we want. We will put probably, this will be the inputs, although this is normally where you put the screw, or you can put the screws here, so we can really have the input here, the cable here. This will be the inputs, the other side will be the output, so we don't confuse both of them. And there is plenty of space in this box. We will just check how much space there is. And this is also, well, it won't be anymore. It was a sealed enclosure because we will have holes for the connectors. It won't be sealed anymore, but it is really sturdy, which is good for the place I will install it in, because things get shifted around. Oh, wow, there's even a UL listing on the inside. Here, there was I had a project, oh, there's even inputs, I don't know what this was. I don't remember, this was an old project I used in, and I had this thing to put the electronics inside. So these are, I have to remove them. Yeah, these things did hold the PCB. I'll show you. I have more of them, and we will use them. Here. You use this thing and you can plug the PCB inside. So we can use one of the PCBs, even if it's not the right one. Can still use one of the project PCBs because the holes are fitting correctly. So normally you just slide it here, and this allows you to hold the PCBs correctly in place. Can we use one of these, or is it too large? Let's remove these devices. Up. So we have a solution. We cannot use the SCR without external power. Since we use external power, let's use the dimmer module. Up. Up. So many meanings of glue. My bin is under the table. Up. Dun, dun, dun. So is it large enough for a project PCB? Oh, there are even slots on the side of the board. There are even slots, so it's for PCBs. A bit larger than PCBs, but it could hold a PCB. It cannot hold this PCB. It's too large for this one, and yeah, it goes inside. It doesn't go inside straight. There are even actually there are even holes here. But if you have a PCB, if we have the right PCB, we could make holes right here. So our project PCB can't be used. So it does fit, but only from an angle. But because of this angle, I cannot use these spacers, because the spacers would not have enough space here. So no, our product PCB, we have to use something else, which is not too much of a shame. We have proto boards. Just need to find them. I don't use them very often. That's all I have. They're not very large. Here I have a bag of boards. So we'll put this on the side. We'll use it later on. See, this thing is getting cramped already. We don't use this anymore. We'll put it to the side. The SCR, we can disconnect it. We won't use it anymore. Meaning for now we can switch off the power supply. Let's put the SCI on top. It's not in the way of anyone. That's for later. That I won't use anymore. This comes documentation tech. This goes here. So I do have these proto boards. This is not the largest, but it's probably large enough. So we will have the holes are a bit too small on this thing, so we'll have to increase the holes so we can fit. As large as I have this. This is the largest I have, and this is not large enough for this thing to go on the side. This way not. We could use. It is large enough for the two holes. No, it's not large enough for the two holes. Either this way. So we cannot use the mounting points inside here because our board is not big enough. I do need larger boards. So we need something where we can put everything together. A large enough board. This is so huge, this module. Can we put something like this? This is the connector, that's for later on. But the connector, we'll need something else with the connector. We cannot use this connector because we would need to have this connector to the PCB here, but the PCB is not close to this border. Meaning we need connectors where you just plug in. Let's check first if I have boards where I can put everything together. So that will be, no, leave it here, because it's a pain to rid of. I'll just use another one. Up. So, enough space for this module. Shitting me, it's not using 100 mil based grid. No, it's not. We will cheat. And for this, it's not high. This is too high. We will have to change. We'll have to change the header so we have a 90 degrees header, allowing us to put it somewhere here, because we want this to hold. We still want this to hold. There will be there's a heatsink. There will be any there won't be any fan or something like that, but we are not dissipating. The motor doesn't need a lot of energy, so we don't need to dissipate too much power. AC is actually on this side, so AC will be on this side, this way almost. With AC dangling, that will be the inputs. Put it this way. If we put it, I just want to see if does it fit in the case. If it's no, it doesn't fit in the case. Although the case, no, it does fit in the case. The case has some foam. I think this is stuck forever. And it's not much of a problem. Here, there's some foam which puts on it, puts a bit of pressure, but not too much. Yeah, I know, I'm checking if it works with the final board, although I didn't even start having the code and the prototype on the breadboard. So what? That would be the inputs. We have the issue again with the microcontroller. We want to be able to flash it, meaning we want to be able to access it, so we will have to have the connectors on this side, or on one of the sides, and not here. And even on one of the sides we have the issue here, actually we can use, that could be cheating. We could use the studs, which are not here anymore. I could use the studs directly on the board. Here we have holes. We can only use 2 because there's not enough space for a third one. But yeah, this way we can connect microcontroller here. Open the ports so we have access to microcontroller. We could cheat just cutting the studs or the standoff holders so it fits on 4 sides, so it's stable. Yep. Oh, we need V in, that's for sure. This is not big enough. We need this one. Okay. Yep. Here we can. Yeah, we could put the studs here and in the middle. So that's not for much of the standoffs. Then we have the output. V out could be next to V in, something like this. We need to connect cables directly here. I will solder cables instead of having through holes, I think. This way. And this would be something like connected like this. No. Let's put it the other way around. It should be something like this. So we have the pins next to the pins. The power will go to the power. And something. Yeah. Can we put a socket? That would be better, so we can switch and unswitch the thing instead of having solder it, because if we solder it, we can put it on this side. We have plenty of space. No, don't have so much space though. Okay, we don't have a limited amount of space. I would like this heatsink. I still would like this heatsink to be not over the board, but flapping somewhere in the air, so it has still more ways to cool down. Yeah, we can solder pins on the side, so we can slide this thing on, at least on this side. On this side we can't, I don't have any pin headers which are big enough for that. Here there will be cables directly going to whatever we need. So we could slide it this way, but it's too large. Always a pain to find the solution. Slide it this way, so it's still in the air, and have this module go somewhere like this, or like this. Will we solder on the cables on the pins? Yeah, I think we'll solder. We could solder on the board directly the cables for the motor, but I think we will solder them on the pins. So it's easier to unsolder. It would be nice to have something we can connect to. Do you have something? Do you have a connector for that? It's perfectly here, but this one has only 2 connections and not 3, obviously. Doesn't fit here. And the pitch is not the same. don't have something which is such a large pitch. I think we'll solder cables directly. Maybe dominoes? No. Up. Yep. So let's do it on the breadboard first. Not sure if the breadboard is meant for 200 volts and the input, so we will have the 200 volts coming from the side. Up. Ah, this is a 200 mil space thing. That's fun. So we have, let's remove these things. Check. We can do it this way. Here we have cables for the motor. Here we have the inputs. Here we have the microcontroller. That will be our setup. I will put this back into the battery management because we won't use it. It cannot provide enough energy. For our device. This is too small. Yep. Let's put it back in our bag. That's the case. How do you actually mount these things? I wonder. I think this is salvaged because connect the cables between them, but how do you mount this on the board? There's nothing. Here you have the connection instead of this things, but I have no idea how you would mount. Glue it simply. See any mounting things? 125 volts. This is rated for 250. It's not written on here, but I think it is. But we won't use it. Still, I wonder how you mount these things on the board. Not a problem. Up. To put them closer. So BCC around. I think this is, I hope this is 3 volt compatible. Most of the optocouplers use just LEDs, LEDs being 1.8 volts, the red LEDs being 1.8 volts. So they should be fine with 3 volts. Here we have the pull-up, which goes to between VCC and zero crossing. So the zero crossing is pulled up. I don't know how it looks like, how the zero crossing looks like. This is what we'll do now. I don't know, because we'll need that for the code. So, up, that's the inputs. The other would be the outputs. We don't need the SCR anymore. Let me show you what I'm doing. is removing the SCR. We don't need this anymore. This put it somewhere where it's not in the way. This will be for later. We can put it in the case. This is for later. Let's put it in the case. Let's put the module back in place. Before we do a final project, we want to test everything on the breadboard. So this will be the inputs, and we will do something which I said is not good to do, but we will still do it. This will be that's one after the other. Because I don't have any clamps, so we will use how are they called? This crocodile clips. One after the other. Let's test the module. It says it can provide 5 volts, 0 to 6 ampere. It should be plenty fine for what we're doing. Let's move this closer. This one will be far away, so we need to move this closer. Yeah. Because I don't have long cables anymore. So we will have, it's not seated correctly. You go in the middle. Up. White is ground and red is 5 volts. Let's measure before we do it if it works correctly. Up. V minus is, yeah, on the side. This is V minus, so it would be ground. Let's put red. I can use shorter. V plus. That should be 5 volts outputs. We need voltage input. And this is what we will do. Do I have other colors? No. We will use crocodile clips up for the input. It says AC, it's not important which was neutral and which one is line. What is important is not shorting the cables, so we will put the leads, we will put the sleeves as much as we can here, so it doesn't short together. Come on. Okay, that's as much as this one can. But the other one is protected, so it should be fine. I'm more afraid of this part. Up. We don't want them to touch. Okay. What we can do to avoid them touching is having everything. Oops, see, something like that. Don't want cables to flap around and breathe when you have high voltage and potentially a bit of current. So we will tape them on the board. So there's less chance for getting contacted together. Up. Okay, now they should move. And did I connect the correct thing? Yeah, this is the power plug. We don't need it for now. The multimeter is still connected to the leads, to the crocodile, but we have to connect the crocodile to the board. And now if we connect to power, we should have 5-volt outputs. Yeah, we see, oh, still have the multimeter. And is it still working? Yes. 5-volt output. At least this module works. Now let's disconnect this. No, I can actually. Let's leave it connected. Shouldn't be a problem. We're at 5 volts. Connect ground first. Connect 5 volts afterwards. The LED is staying on. Oh, but you see there's a dip. We are not at 5 volts anymore. We're at 4.5 volts. Which is weird. Ah, that's the output. No. V in. That's raw input. It's after the diode, so it shouldn't be low. It should be at 5 volts. It seems this one is not. I don't know how much power it provides currently, but 5 volts, 0.6 amp. It doesn't. This draws only 75 milliamps. We are still at 4.6 volts now. That's weird. Is it good enough? Oh, that would be a shame if this one can provide enough current. Is it enough for the board to survive? Let's see if I see VLED on the Wi-Fi. So, VLED up. Okay. The access point is here. So it seems to be good enough, but I expected it to provide more than this. To be a bit better than this, because this only draws 75 milliamps, which we measure. Let's say 100 milliamps. And this transformer says it can provide 0.6 amps at 5 volts, so 600 milliamps. We're not taking 600 milliamps. Still, we are dipping at 4.6 volts. Luckily, we need anything which is above 3.6 volts because of the low dropout regulator, which uses something like 0.3 volts and needs more. I think we should be fine. I'm still surprised it is as low, but which should be fine. So power works. That's a good thing. And it is completely isolated. We don't have any issue. We can touch that as much as we want. The advantage of this brick is it completely isolates the AC from the board. So, and here and on this module we also have the isolation. Let's see how the outputs of the things looks like. So we need to provide 3.3 volts because we want to provide 3.3 volt signals. So ground, let's use orange for 3.3 volts because it is less red than the 5 volts. This LED is still blinking. I don't know if this is because of communication or because it is resetting. I hope it is just a communication. Ah, come on. Yeah. We connect this on the end, so we will have the ground will be the last one. Ground is the last one. I think how this device works is that it's not pulled up. We'll see if we need to provide how low. Orange, sorry, got 3.3 volts. Orange. We will use green as the first signal, which is zero crossing. We want to check how the zero crossing works. And I don't have any other colors, so we will also use green for the next one. Oh, do I have another color? Black, white. No, I don't have any other color. I'll use white, although this one is not ground. I'll still use white. this way. Now if we connect it, yeah, it should be fine. Still working. I want to see what the output is. If what is pulled up and so on. And we still need to connect AC on this thing so we can have an output. Can this be? I think I checked already. No, I have all the terminals. I don't like it that much, but we'll still use crocodile clip. So let's disconnect it and let's connect the solid state relay. No, solid state relay, the triac. So we will use the same colors. This is white is live, so it's in. Another one, yes. It's getting a bit confusing now. Power, go away. Up. No, we said live. Brown. 1, 2. And try the live is connected. It is holding. Not an ideal solution, but it is holding. And enough crocodile clips. Else we can seal cheat. Do we have a second yellow one? No, I only have green and black. So we will have this is the line in. It will go to line in here. We'll use some extended cables, extension cables. Where are my extension cables? Female, male. Here, DuPont wires, female, male. I need one with 4. No, it's female, female. Yeah, female, female. Probes. DuPont, female, male. Something with 4 wires, perfectly. It says 4 wires. This is, everything is disconnected, okay. We don't want to move this too often because there will be power on it. So let's connect it directly so we don't have to touch it afterwards. Up. Dun, dun, dun. Dun, dun. My tape drawer. Up. Scissors. Come here. Let's tape it to the bench so it's not moving. Okay, that's not taping. And this tape doesn't work well. I expected more from you. Up, tape, tape. Okay, this one doesn't move too much. Still need to access this pin. Okay, this will be the inputs. Oh, neutral is this one. Wait, neutral is blue. This, I did something confusing already. Let's do it correctly. white will be neutral, because this is what we have most as cables. So white will be neutral. One, two, and three. Then we have life on yellow. So any colors. Life will be the input. Life is the input. I like to put more sleeves on the things so it doesn't short. And on the outputs we have this. This needs to go here. This goes here. Now we have the right connection. This is right. This is out. Yeah, out, in, neutral, neutral, out. Okay. Now if you connect it, it shouldn't make poof. I hope it doesn't make poof. And let's tape it so this cable doesn't move. And the lamp should not light up. Okay, tape, everything fine. Let's connect it. No poof. That's a good start. And oh, there's an output. Okay. Oh, that's weird. How can I show it to you? Oh, using the cam here on top. Maybe you cannot see, but you can see. But if I switch on the power plug, the power plug lights. Yes, the switch on the power plug has some light, meaning there is some power going through, although there shouldn't be any. Now, if I switch on the lamp, is the lamp still? Where's the lamp? This thing, you can still see it. Yeah. If I switch on the lamp doesn't go on. So there is a tiny bit of residual current going through the triac, but not enough for the lamp, just enough for this tiny light which is inside here. That's fun. Didn't expect that. Now, multimeter, oscilloscope. I want to see how the zero crossing signal looks like. DC, switch to this camera. DC, no, not IC. DC, you didn't switch. And actually the HDMI grabber doesn't grab anything anymore. Come on, HDMI grabber. Did the HDMI grabber die? No, we've seen other things. At least on USB it didn't die. Oh, lots of things died. Lots of things died. I don't have connection to the multimeter anymore or to the power supply. something did crash the USB hub. If I disconnect and reconnect, will it find it again? Yes. Can I switch so the grabber tries to open the grabber again? Bench. Let me try to fix the grabber. So the grabber should be back online, but I think OBS has an issue with them. OBS, can you try to not? Can you try to restart them without having me to restart the whole stream? I tried to grab us with outside of OBS and I could access the streams, and I see that it doesn't start the grabbers. Is there something which says reload? No, you're not reloading. OBS has issues. Okay. Well, I need to start. I think I need to restart OBS. Drop frame 0. Yeah, I'll use this for a pause. I will be back in something like, yeah, I'll be back later today. I'll take a pause. We have 3 hours. Yeah, I need some kind of pause. I'll leave the setup as it is. I'll just shut down OBS, take a bit of a pause to clear my mind, and then we can continue the work with having a DMX control DC motor. I think it will be something between 15 minutes and half an hour. See you later.